Hello, my name is Farhad Pakdaman, and I will be presenting our paper named FRAME-SDN, a fair resource allocation for multiplayer edge-based cloud gaming in SDN. So while cloud gaming can have many benefits for both players and game providers, it faces two main challenges. First, it needs a high bitrate to send a high-quality video to the players. For example, Google Stadia's report shows that transmitting game video at HD quality requires up to 20 megabit per second of traffic, which is a large number. The second issue, which can be actually more challenging, is the low delay requirements. Unlike the normal video streaming, game is something which is interactive and the users need to react in time to the events that are happening in the game. So a high delay can severely affect the user's quality of experience. This can even become more severe in multiplayer cloud gaming. When you are playing with other players in the same game and you're interacting, it is very important that you should have a similar delay and similar game condition. Otherwise, the game is not going to be fair, and some of the players who feel the delay more than the others are going to leave the game probably. So how should we solve this problem? First, we know that the current cloud servers are unable to provide the required delay for all players. That's because some of the players are closer to the cloud server and some of them are far away from the cloud server. And the cloud server can become really congested if the size of the network, size of the service, and the number of players increase. So we propose to use the edge servers, some smaller servers with lower processing power, but somehow that they are geographically distributed so that they are closer to the players and the end delay can actually be decreased. Another thing is that we should monitor the network and be aware of the status of the network and be able to control the network in a central manner so that we can balance the delay between different players who are playing in the same game group. So we use the software-defined network for that, which gives us the overall view of the network and the ability to control the network centrally. With this motivation, we propose a network architecture that combines the cloud servers, the edge servers, and the concept of SDN. So here we have the cloud servers, which are responsible for receiving the game commands from the players and enforcing the game logic to the edge servers. The edge servers are responsible for rendering the game graphic and compressing the video and sending them to the end user. And we have the SDN controller, which has an overall view of the network, which is connected to the network devices, can read the network status, the amount of delay, the remaining bandwidth of the links or the servers, and it can enforce the policies to the network. So if the player requests to play a game, the cloud server is going to calculate the required delays and required bandwidth for that player, and it's going to send it to the SDN controller. The SDN controller reads the network status from other networks devices and eventually is going to run the resource allocation algorithm that we're going to talk about next and decides which edge server and which path are more suitable for this game, and it's going to allocate that through the OpenFlow protocol. Having such an architecture, the goal of this research would be to propose a joint server and path direction algorithm such that the interplayer delay is minimized while the delay and bandwidth requirements for all the players and all the games is satisfied. So to do that, first we define the network delay as the sum of two components. First component is this d of fj, which is the delay from the cloud server to the edge server, and the second part, d of ji, is the delay from the edge server to the player. So this will be the network delay, and we also introduce the interplayer delay, which is the maximum delay between a player and all the other players who are interacting with that player in a game group. So having this, the objective would be to minimize the sum of interplayer delay such that the network limitations are respected and the requirements for each game and each player is satisfied. We need to solve this optimization problem. And this optimization problem actually can become really complex when the size of the network or the number of players, meaning size of the service, increases. So we propose to use a combination of a heuristic algorithm and a genetic algorithm. Every time a player wants to join the network and play, we use the heuristic algorithm to assign network resources to that player. This algorithm is very fast, so which is very good, and it can be run every time. But it is a greedy algorithm and can only find a local optimum. Uh, in specific intervals of time, we use the genetic algorithm to optimize the network, and this algorithm can be a bit slower, but that's a better algorithm that finds the suboptimal solution and considers the whole network instead of a local optimum. The heuristic algorithm is actually very simple. First, it finds all the eligible paths. Then, if the player is requesting a new game group, it means that it's the only player who's playing that game. So the path with the lowest delay is going to be chosen. Otherwise, if it's requesting for a game group which exists, it means that there are other people who are playing. So we will choose the path with the lowest interplayer delay. About the genetic algorithm, one of the most important elements of this algorithm is to have the criterion to choose the best solutions from the population. But what should be this criteria? As we are trying to reduce the interplayer delay, we will define the cost function as the sum of the interplayer delay for all the players. But something that we need to consider here is that imagine that the heuristic algorithm first chooses this server to serve this player, and then we run the genetic algorithm after a while, and the genetic algorithm decides to use this server. So what should we do to change this server? We need to have kind of a service migration. So all the information, all the status is going to be needed to be transmitted from this server to that server, and that can be a very costly process. So we need to have something like a migration cost to penalize this action, to try to reduce it as much as possible. So we will define this migration cost, which is actually the delay of the shortest path from the first server to the second server. And we also add an extra penalty in case the interplayer delay of the second solution is larger than the interplayer delay of the first solution. So this will going to be the cost function that we use for the genetic algorithm. This is a simplified graphical view of the genetic algorithm. First, an initial population is going to be generated based on the heuristic algorithm. Then, in each iteration, first we select a certain number of individuals with the lowest cost, which is the cost function that we defined in the previous slide. Then, these best cost solutions are going to go through the crossover and mutation operation. It means that each random pair of these solutions are going to go through the crossover and the mutation operation, which will generate new solutions. From these new solutions, if a solution satisfies the requirements of the optimization problem, they are going to be selected to form a new population. And finally, we will just add a few number of the best solutions from the previous population to this new population, just to make sure that the best population are not going to be vanished through the iteration of this process. So this process is going to be iterated for a maximum number of iterations to form the best solutions. So finally, we will evaluate this solution in an environment that consists of the mininet as the network emulator, the floodlight SDN controller as the SDN controller, and we imagine to have 100 players, 10 edge servers, and we repeat the experiments for two games, League of Legends and Battlefield 3, which are actually from different game genres. The first one is a battle arena and the second one is a first-person shooter. And this means that they have different requirements. The first one can tolerate up to 300 milliseconds of delay, but the first-person shooter one, you can see that only tolerate 150 milliseconds. Also, we consider a scenario that the players enter the game using a Poisson process. The total time for the simulation is 500 seconds, and every 2 minutes we're gonna update the network status with the genetic algorithm. Between the two genetic algorithm, of course, we use the heuristic algorithm. And finally, we repeat all the experiments for the FRAME-SDN, which is a proposed solution, and a heuristic algorithm, which is presented in this reference from the Amir et al. So here we can see the average delay for the FRAME-SDN and the GRH algorithm. So at the beginning of the simulation, the heuristic algorithm is used to allocate network resources to the newcomers. And you can see that it behaves almost the same as the heuristic algorithm in the GRH method. But at the time intervals of 2 minutes, here you can see them with the dashed lines, we call the genetic algorithm. And each time the genetic algorithm is called, the delay falls rapidly to some kind of constant delay. So you can see that we are actually much better than the GRH, and on average of all the times, we are 20% less delayed than the GRH algorithm. It's almost the same for the interplayer delay. Again, you can see that at the beginning the heuristic algorithm is used, but every time that we call the genetic algorithm, the interplayer delay rapidly falls to something close to zero actually. And actually always the interplayer delay is below 50 milliseconds, which is very small number and is not actually perceivable for most of the players. Another observation is that how the genetic algorithm evolves through time. For the GRH, you can see that when the time passes, it becomes actually very large, but the genetic algorithm here allows us to remain somewhere close to the zero every time we call it. So as the time passes, the difference between the GRH algorithm and the FRAME-SDN becomes more apparent. At the last moment of the simulation, we are 31% smaller in terms of delay and 94% smaller in terms of interplayer delay compared to the GRH, which actually leads to more fairness, something that we can see better here. We measure Jain's fairness index. The higher index shows the better fairness, and you can see that for all groups of player, FRAME-SDN performs much better than the GRH for all of these groups of players. And finally, we measure the computational complexity for the numbers used in this simulation, meaning 100 players and 10 edge servers. We are 34% less complex. And more importantly, this solution scales better when the size of the network and the number of players increases. For 500 players and 20 edge servers, we are 69% less complex compared to the GRH, which is very good news because this shows that it can work much better for the large services which are more realistic. So in conclusion, we show that how joining the edge computing and cloud computing can benefit the cloud gaming, and we show how using the SDN gives us an overall view so that we can balance the interplayer delay and the delay for all the players, and we show how we can formulate and solve this problem as an optimization problem such that the interplayer delay is minimized and we still grant the required resources for all of the players. So that's it. Thank you very much for watching. Please do not hesitate to contact us in case of any questions. Thank you.